Hello and good day everyone. My name is Ron and let us answer some thermodynamic problems. So, this problem is inspired from problem 7.15 of the Introduction to CHE Thermodynamics 8th edition by Smith, Van Ness, Abbott, and Swihart. So, this is not the exact problem, but it is a modification of the problem in itself in order to accommodate for this lecture today. So, this modified problem is stated here. A steam turbine operates adiabatically. Steam enters the turbine at 2,400 kilopascals and 500 degrees Celsius and exhausts from the turbine as saturated vapor or 20 kilopascals. If the steam rate through the turbine is 100 kilogram per second, what is the total power output and turbine efficiency? So, to start, we need to begin with the diagram and the given. So, the steam enters, superheated steam enters the turbine at the inlet pressure, temperature, and the mass flow rate 100 kg per second, and exhausts as saturated vapor in the outlet at 20 kilopascals. And the turbine details is that it operates adiabatically. That's it. Our required is the turbine efficiency, or eta, and the total power produced by the turbine, or negative P. I'll explain why negative P. For now, the solution will be as follows. I will start solving it first by hand, then we will simulate it using DWSim and compare the two if they match results. So, to start off our solution, we need to define the assumptions for the entirety of the system. We can assume steady state such that the inlet molar mass flow rate is equal to the outlet mass flow rate, meaning that M1 is 100 kg per second and M2 is also 100 kg per second. Next, at constant flow speed, meaning that the fluid is traveling through the unit operation at constant speed, constant velocity. This means that kinetic energy is equal to 0. Next, we also assume that the system is at ground level, meaning no height change. This means that the potential energy is also equal to 0. Next, for the unit operation details for turbine specifically, its work is produced work, and it is specified by chemical engineering connotation as a negative symbol. Produced power is negative P using this formula such that we will only multiply the produced work by the mass flow rate. The maximum produced power is the shaft work at isentropic conditions, and unless stated, it is adiabatic. And since it is already stated as adiabatic, then we can say that Q equals 0. It is satisfying this assumption. Lastly, the turbine efficiency can be defined as the actual power produced over the maximum power produced, or substituting the formula for power, which is shaft work times mass flow rate, cancelling mass flow rate, we have that the turbine efficiency is also equal to the actual shaft work produced over the maximum produced shaft work, or at isentropic conditions. Then, to start off, we just need to first start with a steady state open system, energy balance, one inlet, one outlet. So these two will equal to 0. These three, will equal to 0. Then remember, shaft work must be negative to represent produced work. Then we'll have a negative change in enthalpy, which means that rather than outlet minus inlet, it is essentially inlet minus outlet. And this is our first equation. In terms of isentropic conditions, the outlet at isentropic condition is subtracted from the inlet enthalpy, which yields the maximum produced shaft work at isentropic conditions. Or in order to get the maximum produced work, it must be identified and calculated at isentropic conditions. So, we need to find the inlet conditions of water. So, water is acting as superheated steam, initial pressure, initial temperature, and we need to find its enthalpy and entropy. How do we do that? So, we just need to go to the steam table of Smith, Van Ness, Abbott, Swihart, 8th edition, and we need to use these two properties in order to determine the enthalpy from its very own steam table. So using it, we found out that its enthalpy is 3,462.9 kilojoules per kilogram, and entropy is 7.3439 kilojoules per kilogram per Kelvin. And this is proof that it actually came from the steam table from Smith, Van Ness, Abbott, and Swihart. As you can see in the highlighted parts, 2,400 kPa, 500 degrees Celsius, and this is where our H enthalpy and S entropy. Next, we need to find the outlet conditions at real scenario. Not isentropic, but real scenario. So we already know that it is a saturated vapor exiting the turbine, and it is at 20 kilopascals. So we don't need essentially the temperature because we already know it's saturated vapor. We just need to focus on the saturated steam table. This table here is a superheated steam table, but in here it's just a saturated steam table. So we need to find the saturated steam properties at 20 kilopascal. So using this connotation, we found out that the outlet enthalpy, true outlet enthalpy, is 2609.9 kilojoules per kilogram, and the true entropy is 7.9094 kilojoules per kilogram per Kelvin. Though it is in the same superheated steam table, in order to assist on our acquisition of the data, it's in the superheated steam table. It also provides for a given pressure. It is already provided with a saturated temperature. So at 20 kilopascals, the saturated temperature is 60.09, and at saturated vapor, so we also define that it is at saturated vapor, and it is already given here. Then the enthalpy is 2609.9 and 7.9094. Then we need to find the isentropic conditions because we need to find the efficiency, and in order to find the efficiency, we need to find the maximum power produced or the maximum shaft work produced, which means that we need to identify it at isentropic conditions. So what does isentropic conditions mean? This essentially means that the entropy at the inlet is equal to the entropy at the outlet. S1 equals S2S. Hence why we assume that though it is already given that the outlet pressure is 20 kilopascal, the outlet entropy, rather than 7.9094, it is 7.3439, the same as the entropy at the inlet. So how do we find out the enthalpy of these certain conditions? Well, we use what we call the quality method. So using the quality method, using this formula, where to find the outlet entropy is equal to the fraction at vapor times the saturated vapor entropy at outlet pressure plus the outlet liquid fraction times the saturated liquid entropy at outlet pressure. Then how do we find out this XV and XL? Well, XV is simply 1 minus XL, so we have one unknown, one equation, simple algebraic method. We found out that the fraction of liquid is 0.0799. Then, in order to find the enthalpy at isentropic conditions, you use the same quality method under the same connotations such that S will be changed into H. We already know XL, so we just convert this same formula, XL. We have this is all defined, and this is unknown. Simple introduction to a calculator. And the isentropic enthalpy is at 2421.4523 kilojoule per kilogram. And this is the superheated steam table provided, and this is the highlighted parts. Then, how do we find the actual power produced? Remember, in our steady state energy balance equation, the actual power is simply the inlet enthalpy minus the outlet enthalpy for shaft work. But for power, we multiply everything by the mass flow rate in order to change this term into a power term. So essentially, the power produced in the turbine is simply the inlet enthalpy minus the outlet enthalpy, all multiplied by the mass flow rate. So substituting H1, which we calculated earlier, and H2 at actual conditions, we found out that the true actual power produced is 85,300 kilojoules per second, or 85,300 kilowatts. Then for the turbine efficiency, how do we find the turbine efficiency? Remember that our final derivation of the turbine efficiency is that the efficiency is equal to the actual shaft work produced over the isentropic or maximum shaft work produced. Then, knowing that shaft work is simply inlet enthalpy minus outlet enthalpy, and for isentropic conditions, it's the same formula, such that the outlet enthalpy is at isentropic conditions, and since we already know the inlet enthalpy, the outlet enthalpy, and the outlet enthalpy at isentropic conditions, it is a simple substitution method, and we got a answer of 81.9052% efficiency of the turbine. So, this is our final answer using handheld calculation, and then let's solve this using simulation. So going to the process modeling, create a new process model, wait for it to load, and then we go back to the problem to assist you in this course. So click next, then we'll go, what is the property here? Steam, and steam is just water, so we'll just click here water. And property package is steam table. So steam tables here, we add them here. Next, system of units. So the pressure is at kPa, kilopascal. Sorry, we need to create our own. So kilopascal, then temperature is at Celsius, and mass flow rate is kilogram per second. Then pressure change is also kilopascal. Pressure difference is also at kilopascal. Then finish. Alright, that's it. Then for the reference problem, the diagram, let's focus on the diagram. So steam turbine is pressure here, pressure changers and expander, and DWSim will automatically provide the details for the diagram. Next, for the outlet, for the inlet, sorry, we need to rename it properly. So this is the inlet, and this is the outlet, and this is the energy produced. Sorry. Okay, then the inlet condition is at 2400 kPa and 500 Celsius and 100 kilogram per second. Then lastly, steam turbine must be adiabatic in nature. So adiabatic efficiency, and we need to have an outlet saturated vapor. So the outlet must be at 20 kilopascal, sorry. Outlet pressure must be at 20 kilopascal. Okay. Then how do we, so we need a efficiency value. So we already calculated an efficiency value, and using this value we need to check if the value we calculated, these are connected in a way. And we need to check if when we input this value in DWSim, it must spit out the same or similar value. So when we include an efficiency of 81.9052% efficiency, according to DWSim, the energy produced by simulation is 85,350.77 kilowatts. So 85,350.77 kilowatts. And how do we know if our answer and the answer from DWSim is similar? We will use a percent difference method. So the percent difference between the calculated and the simulated uses this formula. The calculated minus the simulated absolute value over the average of the two values. Noting that the calculated is our calculated is 85,300 kilowatts. Okay, then our simulated is 85,350.77 kilowatts. Applying this percent difference formula, we get a percent difference of 0.06%, meaning these two values are very, very close to each other, that any certain difference representing them may be considered negligible. This means that we have proven that through simulation and through hand calculation, our answer is accurate. Thank you.